Okay, so welcome back to another video. So today we're dealing with a limit of, inside of our limit is that we actually have the swinging factorial. So we want to evaluate the limit as n approaches 0 from the right side of the natural log of the swinging factorial of n divided by n. So this is like the third video I talked about the swinging factorial. So I'm just, for anybody still new, and are not aware with this notation, so the swinging factorial if n is defined as for n greater than or equal to 0, we have that this is n factorial and then divided by the floor of n divided by 2 factorial quantity square. Let me actually put in this little condition as well. I already said that. So we're actually dealing with a limit this time, and it's actually, the computation's a bit straightforward because you just, plug in the swinging factorials, this definition over here, back into our limit and then solve from there. However, going through midway through solving this problem, there's actually going to be a little bit of an issue that, well, I guess this is more on personally from me that I'm going to explain, and then I guess I'll just put some little justifications on like why we can actually make this without me having to like go over the whole, because there's some parts of the problem that it's actually really difficult to explicitly, show that work, and you'll see why once I get into it. So other than that, we got a couple formulas that will also be to look out for as well. So let's actually just jump right in. So if we have this definition over here, so let's actually just plug this back to our given. So hence, we now have the limit as n approaches 0 from the right of, now I'll just replace this, this denominator for n, I could just write that as 1 over n, and then multiply with the ln of the swinging factorial of that definition. So now that would be the natural log of n factorial, all this being divided by the floor of n divided by 2, and then factorial, and then quantity square. The parenthesis doesn't end there just yet. And so now what I can do is we have both inputs of a numerator and denominator of the natural log, so we can actually use the rules of natural logs of division and actually take a subtraction of these natural logs. So now we would now have the following. So the limit n approaches 0 from the right, and now also with this, I'll have to distribute the 1 over n into each as well. So let me first denote this big parentheses. So now we have 1 over n, then multiplied by the natural log of n factorial, and then this is subtract. So there's an exponent over here for 2. So we're using rules of natural logs that comes in front of our, that constant will come in front of our natural log expression. So now this will be 2 divided by n of the natural log of the floor of n divided by 2 factorial. Now here comes the issue, but before we get to that, let's actually make a little note here. So it's worth noting that if we take a look at the input for the floor of 2, of n over 2, so the floor of n over 2 is actually going to equal 0, where n is inclusive for 0 and then less than 2. As you can see that everything in between is actually going to be equal 0. So I can write it like this technically. So n is in between 0 and 2, so not inclusive. Anything you plug in between, it'll just be 0. And so with this justification and say that the natural log of n divided by 2 factorial is actually just going to equal just ln of 0 factorial, which indeed is ln of 1, which is just going to be 0. So from there, now let's actually, so this is where the interesting part comes in that I have to bring up this little issue about in terms of the computation. So now if I put all this back, if we're specifically taking this limit over here, so the limit as n approaches 0 plus of 2 times the natural log of n, and then the floor of n divided by 2 factorial, all this being divided by n. So you notice that if you were to take this limit, we have a 0 over 0 indeterminate form. This is where the issue arises. If we have an indeterminate form and we have a rational function, so obviously with L'Hopital's rule, obviously we need like f and g being differentiable such that after if we have this in an indeterminate form of 0 over 0 or infinity over infinity, then we can actually take the derivative of both the top and the bottom. Well, it's no surprise that this is very easy to take the derivative of. However, this kind of leads to an issue for me personally on how to take the derivative of, specifically we're dealing with both a floor function and a factorial itself. So this led to some difficulty for me on how to actually calculate the derivative of the numerator. So I had to resort to, well, before I get to that, it's more of, there are several ways that I try, mainly because I know that there's a factorial that I was thinking that we can actually apply maybe the gamma function or some relation with that. But that clearly did not work. And including with the floor functions, I've tried my best to actually try to research on how exactly we could take, take the derivative. But as you see with floor functions, it's not continuous and, it's not differentiable at those points where the discontinuities, appear. So that's quite a bit of an issue. So I had to lead to this resort and actually plot this function specifically into Desmos, a graphing calculator online that anybody can use. And if you were to slowly see this graph, and if you take this limit as it approaches 0 from the right, it's also worth noting that anything on that graph from 0 to 4 on that interval is actually going to be equal to 0. If you think about this, as I mentioned, that the definition what we wrote is that n divided by 2 is equal to 0 for anything between n from 0 to 2, not inclusive. But also, if you were to take a look in for anything for 3 and 4, you'll notice that those floor function, the floor function of that is actually going to equal 1, hence where it's ln of 1 factorial, which is still equal to 0. When we take this limit, you'll notice that from everything from 0 to 4 is going to be equal 0. So initially, it's almost like saying you're taking the limit as n approaches 0 of 0 divided by n. So even though, because we already established that ln of 0 factorial, which is from that numerator, is equal to 0, but as we take constants, going backwards, approaching towards 0 plus, it's slowly actually going to approach 0. So that's hence my justification to use. And obviously, I'm going to put that the OBS simulation of how the taking this limit of that function is going to look like. So hence that's the way, that's my backup without having me thinking that I'm making this up. Nope, it's I've done everything I can, and then graphing this was the only way I was able to like visually see like what number this approaches to. So that's where we're at. So even with this the case, so that means if I were to write back this limit of the same thing, so the limit n 0 plus, so if I write back the same thing and then ln of n factorial, then subtract 2 divided by n of ln of the floor of n divided by 2 factorial, then that means the justification is saying that from Desmos that I have to graph this out, is that this limit over here for this function over here is actually going to approach 0. So now what we're really left with is to evaluate this limit. So now let me actually write this again one more time. So now we have the limit as n approaches 0 plus of, now we have ln of n factorial divided by n. And then what you'll notice is that actually this is also in a form of 0 over 0. So indeed we can actually take the derivative of this, but since we have a factorial over here, we can, as I said, mentioned from everything I'm trying, I actually did use the gamma relationship from there to try to explicitly solve, the derivative of the top, but that didn't work. But in this case, you can for this. So what we can use is that this relationship is we can replace n factorial with the gamma of n plus 1. So now this is gamma of n plus 1, and I'll still write this again. This is still, you're going to get a 0 over 0 since gamma of 1, you just plug 0 into here, is equal to 1, so ln of 1 is just 0. But anyway, from here, we can take the derivative of both the numerator and denominator. It's so differential for both the top and bottom. Obviously, we know that this is just equal to 1, so we just have to evaluate this. Obviously, we see that if we take the derivative, we have we would have gamma prime of n plus 1, and then being divided by gamma of n plus 1. But this is very interesting because this is actually the definition of a special function known as the digamma function. In other words, it's the logarithmic derivative of the gamma function. So now I can just replace this with the limit as n approaches 0 plus of lowercase psi at n plus 1. Okay, and now all we have to do is just calculate, if we just plug 0, so this is just psi of 1, which indeed this is actually just going to equal negative lowercase gamma for the Euler-Mascheroni constant. And it's also, you can see this by using the series expansion of psi of n plus 1. So let me just actually make a little adjustment over here and say that you can actually use the series expansion, which just says that this is basically saying the limit as, well, really, if we're taking a look at the series expansion of psi of n plus 1, I just put the limit on the side since this just matches. This is basically, the expansion is as follows. It's negative lowercase gamma, then plus the infinite sum of, if we say k is equal to 1 of the following. So this will be 1 over k, and then subtract with 1 divided by k plus n. And of course, what is it? N cannot be some sort of negative integer. So with this adjustment, because now we can just plug in 0, so everything for 0 here is just 1 over k minus 1 over k, 0. So all we're left with is just negative lowercase gamma, the Euler-Mascheroni constant, which that approximates to negative 0.57721. And as you'll see as I pull up another the Desmos again, as I take this entire limit of our given, you'll see that indeed, as we get closer and closer to that graph, it actually does approach that same value. So there we have it, it's complete. So if anybody is able to calculate the derivative of 2ln of the floor of n over 2 factorial, you know, by all means, please let me know. You know, this will be an interesting learning experience for everybody, that if you'd be willing to share that with us, because this was where I got stuck the most, and I got worried. I'm trying to figure out like how exactly am I supposed to justify it as we continue forward. So that's hence why you see those the Desmos limit, or the graph comparison, to see how the limit approaches of those functions. So yeah, that's pretty cool if you ask me.